Okay, aldehydes and ketones. We're going to look at these two functional groups. They're very closely related, but aldehydes are on the end of the chain and are more highly reactive than ketones that are in the middle of a chain. Aldehydes and ketones both have a functional group, and you see a lot of them in biological compounds. You can see that you have an aldehyde has a little hydrogen on the carbonyl that acts as a flag, and a ketone has a carbon on either side. Notice with this ketone you actually have hydroxyl groups on either carbon. That's okay. That doesn't change this functional group, because the functional group, as long as there's a carbon here and a carbon here, is going to be a ketone. It's only when there's something different besides a carbon attached to either side that it becomes a different functional group. Aldehydes and ketones are named in the same way that we've been learning to name other functional groups. Aldehydes and ketones have a higher priority than alcohols or enes. In fact, the order of priority is aldehydes, then ketones, then alcohols, then alkenes, and then even after that are the alkoxy groups, the ether functional group. You name an aldehyde by giving it an Enol ending, and you name ketones by giving them an anone ending. When you look at the aldehyde group is always going to be on the number one carbon, and so we do not have to put a 1 in front of it. So if we look down here, let's say at the second compound in the table, you'll see that there's 2 carbons. So the systematic IUPAC name would be F for the 2 carbons and then Enol for the ending. There's no need to say 1 or 2 for any aldehyde, and so we don't. If we look down at the next one, you can see there's 3 carbons, so it's prop. Then there's the ene in there, so we're going to call that prop-ene-al. The aldehyde we know has to be on the end, and the ene, really you ought to say 2, because theoretically you can have the double bond on the number 1 carbon, although it's a very highly reactive compound and not very common. If we look at the next compound, you will see there's 4, and so now they do number the ene, and you can see it's 2-butanal. Again, we do not number the aldehyde because it's always number 1. To name the ketones, we're going to end them with anone. So if I count the number of carbons in the chain, for instance, on this first one, I see 6, so I called it hexanone. We do have to number where the ketone is, except for in propanone, in which it has to be on the number 2 carbon, and in butanone, it has to be on the number 2 carbon. After that, you have to place the ketone functional group somewhere in the chain because there's more than one possible ketone. Because in hexanone, you could have it on 2 or 3, we have to name this one 3-hexanone. Notice you can put the 3 prior to the one, as we did with the alcohols and the alkenes. It's more common that you see the number in the front, though. If I look at this functional group, the ene has priority, so we're going to call it 2-one. So this is 4-hexene-2-one because the ene ends up being on the number 4 carbon. If I look at this is going to be a dione because there's 2 ketone functional groups. Again, you number so that we get the lowest set of numbers. So if I number from the right, I end up getting 2 and 4. So this is 2-hexane dione. There are several ketones that have common names, and you've already encountered acetone, particularly in the lab. We use acetone. It's a common solvent. You can even go to a hardware and buy acetone. The systematic name would be propanone, but acetone is what we usually call it. Acetophenone is a common name, and then benzophenone. Those are two common names that are used quite a bit. Ketones and aldehydes can be substituents when they are not the primary functional group. So when it is as a substituent, you will use the term oxo to indicate the aldehyde, and you number to place it somewhere. Later on, we will see that when it's attached to a benzene ring, that you give them a substituent names, for instance, acetyl or formyl or benzoyl, but the naming of these will be reserved for next semester. You don't have to worry about that yet. If you look down at the example at the bottom of this screen, you will see that here the ketone is the secondary functional group and the aldehyde is the primary functional group. So this is named as a hexanal. Then the ketone functional group becomes oxo, and so we name it 3-oxo-hexanal. Carbonyls have a very large dipole, and as a result, they're reactive. Nucleophiles are highly attracted to the carbon with its large del positive and the weak double bond. The pi bond is weak compared to sigma bonds. Oxygens have a large del negative and so are easily protonated by acids. As a result, you're going to find that they undergo a lot of interesting reactions. The reactions that we're learning this semester are going to be very limited, but realize that a carbonyl is reactive. Its large polarity increases its boiling point, and so what you find is they have a higher boiling point than alkanes or alkenes of a similar molar mass. However, they are not as polar as alcohols, and so their boiling point will be lower than that. And that's primarily due to the alcohol's ability to hydrogen bond to itself. And so you have high boiling points for alcohols compared to their molar mass. Carbonyls do allow some hydrogen bonding to water, and so something like acetone we find is miscible in water. If I look at 2-butanone, it has a little bit of water solubility. As you add carbons on, of course, the water solubility starts decreasing. As we mentioned already, there is no intermolecular hydrogen bonding, but it is polar. So the melting point and boiling point are increased over that of the alkanes or alkenes, but it is less than that of the alcohol. There is almost no difference in the melting point and boiling point between the same molar mass aldehydes and ketones. So 2-hexanone has almost the same boiling point as hexanal. Here's a chart showing the boiling points, and you can see the alcohols tend to have high boiling points. Aldehydes are polar, but nowhere near as polar as the alcohols. And the alkenes and alkanes have about the same attractiveness for each other, and so the boiling points are about the same. Ketones are very similar to aldehydes in boiling point, and so you see as we go from one chart to the other, the chart for ketones and the chart for aldehyde, the line for those boiling points remain about the same for the same molar mass. Here are some examples of how to name. The first thing that you do is you have to find the principal chain. That is the longest chain with the functional group in it. And because we have an aldehyde, it must contain that. And we go and trace it to find the longest possible chain, which is 6. So that means we're going to have the hexanal for the aldehyde group. Now we have 2 substituents on there. There are 2 methyl groups. We locate them by realizing that the Aldehyde sets the numbering system. So the methyls are on the 4 and the 5 carbon, so we end up getting 4,5-dimethyl. If I look down at this functional group down here, we see that it has 2 carbons, so that is going to be ethanol. Now I see there's a chloro on the number 2 carbon, so it's 2-chloroethanol. A common way of identifying functional groups on carbonyl compounds is to call the carbon that is adjacent to the carbon the alpha carbon, and so the one that would be 1 over then would be beta, and then you have gamma, etc. So a common name for this is alpha chloro, and a common name for a 2-carbon aldehyde, or the 2-carbon aldehyde, is acetaldehyde. And so a common name for this is alpha chloroacetaldehyde. And we'll next semester use more of the alpha and beta to indicate a carbon adjacent to a carbonyl. That's going to be something that we use when we start. Go ahead and try to name this compound, and also try to draw 4-phenyl-decanal. Pause the lecture and then restart after you've tried to do these things. Okay, so if I look at this aldehyde, I see that it's 1, 2, 3, 4, 5, 6. So this is going to be a hexanal. There are substituents on the 2, 3, and 5 carbons. We're going to say 2,5-dimethyl, and the hot hydroxy is on the number 3 carbon. Then we put it in alphabetical order. Because methyl comes after hydroxy, we will say 3-hydroxyl, 5-methyl hexanal. If I look at this compound, 4-phenyl-decanal, the first thing I'm going to need to do is put down 10 carbons for the dec and end it with an aldehyde. On the number 4 carbon, I'm going to have to put a benzene ring because phenyl stands for a benzene ring as a substituent. So this is 4-phenyl-decanal. Here are some examples of naming ketones. First thing I have to do is find the principal chain. Here's the longest chain with the functional group, the ketone. It's the primary functional group. Aminos, like alcohols, are secondary compared to aldehydes and ketones. So if I look at this, I'm going to name this as a pentanone. Where is the amino group? Because the ketone is primary, the numbering of the amino group must be subordinate to the numbering of the ketone. So it's 2-pentanone and 4-amino. So we call this 4-amino-2-pentanone. If I look at this dione down here, I see there are 6 carbons, so I'm going to call it hexane dione. Where are they located? They are the lowest numbers chosen would give you 2,4, so it's 2,4-hexane dione. If I look at this, you can see the longest chain, of course, is the cyclopent, but it's an enone. So I'm going to call it cyclopentenone, and because the primary functional group is the ketone, it's number 1 right there. The ene must be on the 3rd carbon, so I call it 3-cyclopentenone, and I choose the lowest numbers that would give me 3-methyl 3-cyclopentenone. Go ahead and try to name this ketone and draw the ketone underneath, and then restart the lecture. Okay, for this compound up here, this is 3 carbons, so it's prop, cyclopropanone. The ethyl, it gets the lowest number, but the carbonyl must be on the number 1 carbon, so we're going to choose 2-ethyl cyclopentanone. Excuse me, propanone, my bad. If I look at this next compound, there's going to be 7 carbons, and there's going to be both an ene and an one. The one is on the number 2, the ene is on the number 4, and then on the number 6 carbons, you're going to have methyl groups. And so this is 6,6,4 heptene 2-one. This slide introduces a new term for you, and that is a tautomer. A tautomer or tautomers are 2 isomers of a compound that differ by the placement of 1 atom. And if I look down here at the bottom at the carbonyl compound, you can see that if I pluck this hydrogen off, I can form a double bond with the carbon adjacent to it, and then put the hydrogen on the oxygen, losing the double bond to the oxygen. And these 2 are isomers, and they differ by the placement of only 1 atom. The isomer on the left is either an aldehyde or a ketone, and the isomer on the right is called an enol. And this is something that is catalyzed by acid or base, and we can easily form these in an aqueous solution or even in an organic solvent, which has draw the 3-methyl-butanal enol. So first draw 3-methyl-butanal and then draw the enol form of it. So here is 3-methyl-butanal. In order to make the enol, it's going to be in equilibrium. So I'm putting 2 arrows in to indicate an equilibrium. And this is either acid or base catalyzed. Then I form the enol by removing the double bond and making it into an alcohol and putting a double bond adjacent to that alcohol group with the carbon adjacent to it.